Oh, no, thank you. I'm just gonna feel like I'm dying for a little while. That's okay. I'm here and I'm alive. A little late. Hello, people popping on. I'm sorry I'm late.
Hello.
Hey, hey.
Hey. How are you today?
Mostly dead. How are you?
Fine, thank you.
Okay.
What we have for today?
Oh, your least favorite thing from the last class.
Yeah.
It's gonna be fun. I am gonna wait a few more minutes. One, to catch my breath, and two, to let people log in. Because yeah, I'm a little late, and I expect that nobody expected that. They probably already clicked. I wasn't there, and they probably gave up. So I'm now realizing I could have actually logged in on my phone, and then but if I logged in on my phone on the walk up here, people hearing, "Oh, sir, oh, sir," probably wouldn't have been impressed. Because I am a very, as I like to refer to myself, I am a weak little man child. You know, just oh,
You're here.
I made it. I am alive. I can barely feel my legs. You don't have a mic or video right now. Okay, but you can hear me and see me? Or see the screen that I'm sharing at least? Because I don't care if anybody sees me.
No, yes, I can see.
Oh, there's a direct message to me that I'm speaking to. Did you hear that, Alexis? Yeah, no, yeah. Yes, okay, cool. Nod your head twice if you need help. All right. Cool. Okay. Oh, I'm gonna die. All right. Hello, tall chair. I missed you. Also, I have plantar fasciitis, and it was a great idea to grab my shoes that don't have my insoles in them and not pop them in. So, I'm good for math advice. If you ever have any questions about almost anything else, do not consult me. I am an idiot. Oh, and I know we were talking about computers the other day.
Yeah.
I was watching a video on a tech page on YouTube, and they mentioned a card that was surprisingly cheap on eBay and can pretty much run everything on low settings. That was the RX 580, and you can get a pretty good deal on them. And it has 8 gigs of video RAM, which is pretty freaking decent. So if I was, and I think you might be able to find like a low profile A low profile specific card. There's bracket. Yeah, but you'd probably have to replace maybe the power supply in a Dell Optiplex and slap one of these guys in there, and you got yourself a gaming PC for like $250.
No shit.
Yeah,
Wow.
yeah, you really just got to make sure it's got the guts.
Heck, yeah. All right, 580.
Yeah, that's a pretty decent card. Again, not Optiplex with like an i5 or an i7, 16 gigs of RAM, slap that in there. It'll run everything on low settings for probably a couple more years.
Nice.
Maybe even medium, I don't know. I bought a beefy gaming PC and totally just play like smaller indie games and go back and play Skyrim for the 50th time. That's my jam. It's like playing D&D, but everything's easy and you run around smashing dragons in the face. It's great. It was the only time when I was working at GameStop that I'd actually see the Madden bros that I'd see once a year come in and buy an RPG. And those jerks are still selling it on every system. All right, well, I think 7 minutes into the meeting actually starting. It's a good time to actually start. I think I got a few people and we'll see if more show up. Usually it starts trickling in about 6:30, so. Ooh, that left kidney hurts, all right, so. Should your kidneys hurt when you have extreme physical activity or something? Like that's always been a thing for me. But it is definitely my left kidney. All right. Cool, I'm gonna die. A wound I didn't know it existed after using hand sanitizer. Bonjour. Okay, so for today, so again, sorry I missed Tuesday. Things come up and yeah, last freaking minute, or well, not last minute, but last day. But this is the class I prepared for Tuesday and already had it prepared, so at least I didn't have to go nuts before this class. So today we'll do some review of last Thursday, and then we're going to do a lot of really fun things. Greatest common factor, least common multiple, and more on lowest common denominator, which if you remember is it's the bottom of the fractions when you're adding them and subtracting them. And I'm going to try to keep you from crying over these options. Now, I'm going to give you a bit of a preface before we get started, even on the review stuff. But the greatest common factor and least common multiple method, one, I found a nice method, well, the nicest method I could find. That is pretty much idiot proof if you get the understanding of how to set it up. Because the way I like to do it is really hard to explain. It's easier to understand if you got like a basis of that. So what I'm going to do is as I do these examples, I will kind of follow through with the way that I am intending to do them through these examples, but then I'll also show you the way I would usually do them, and that's with a factor tree, and being able to kind of eyeball stuff. And as we get further in the problems, you'll be able to kind of see that click a little better. But the nice thing is that technically the setup on all of these methods is exactly the same. It's just what we do with them after at the very end is the difference. So it's going to be weird, but it's not going to be bad. Okay. Review, mixed fraction examples. Look, they're word problems, but they're weird, and apparently I never actually finished typing that one out, so we're just going to delete that. Good job, Ben. All right. I wanted something with Batman. All right.
You deleted Batman?
I deleted Batman.
Wow.
Yeah, what you gonna do about it?
Oh, yeah, they.
Why the hell is the speaker coming out of the camera halfway across the room? Whatever. I have patience for this thing today. All right. So these are always my favorite word problems to do in the class because I made them up and I was bored. So Spider-Man ate 1 5/6 pounds of cat food last week. This week, he ate 3/4 pounds less. How much cat food did Spider-Man eat this week? Well, that sounds like subtraction, yeah?
Yeah.
All right. So we got 1 5/6 minus 3/4. Let's jump over to funky looking document camera thing. Ooh, why is my head hurt? That's new. All right. Oh, it's going away. Uh-oh, that can't be good. It's on you guys. If I fall over and die, that door leads outside. Just kick me out there, walk away. Nothing happened.
I'm gonna pull the fire alarm and say it was you when you were falling down.
That's messed up. I appreciate it.
They will get somebody attention.
I appreciate it. That's messed up. I actually kind of hate the fire alarms here. A couple of years ago, they actually went off and stayed on. And all the projectors on this side of the building stayed on, even in some of the faculty offices. And some of the faculty had stacks and stacks of books that they couldn't replace, that they've been building for like decades, and just soaked through everything and destroyed everything. Like they were working on this side of the building forever. Yeah, so,
Wait, so when you pull the fire alarm, these instantly go off?
yeah,
I thought it was just a loud noise to get out.
No. no, but in case you're wondering why these fire alarms look kind of extra shiny and new, that's why. So, yeah,
I'm wondering.
we are not messing with the fire alarms. Whew. Oh, God.
Well, then I'm gonna have to walk around with you in one of these classes to get you participated. Unless you have a tattoo on you that says do not resuscitate.
I'll write it on my arm right now. I'm down. Sharpie it across my chest, like one of those, like full on, like, you know, like tattoo style printing. Resuscitate essay.
What you learned in school today, teacher passed away.
I mean, it happens. Oh, man. Getting my brain to work is difficult. I'm sorry, guys. All right, so we got to convert this guy to an improper fraction. So if you remember, you take that number, multiply it by the bottom. So 1 times 6 is 6, and then you add it to the top. 6 plus 5 is 11. So this is 11/6 minus 3/4. In order to do this math, you need a common denominator. So between 6 and 4, you just think of the first multiple that they both have in common. 6.
24.
Huh?
24?
Who was right,
You-
who was wrong?
Okay, here's the thing. You're thinking actually of what we're gonna go into today, which is greatest common factor. So that's the other way around. 2,
2. Yeah, it's 2.
yeah, well, 24 is a common factor because if you multiply these two together, you do get 24. You could work with that. But if I multiplied 6 times 2, I'd have 12. And does 4 go into 12?
Yes.
So that's one way to do these really quickly is you could start thinking of multiples of 1 and see if the other one can fit into that number instead of finding the multiples of both and just finding where the first one they run across. It'll still work out every time that way.
Yeah.
So we're gonna shoot for 12. This one, I'm gonna have to multiply by 2/2 to get that bottom to be 12. This one I'll have to multiply by 3/3 to get the bottom to be 12. So of course, with the multiplication parts, we just multiply straight across, 2 times 11, 22, 2 times 6, 12, minus 3 times 3, 9, over 4 times 3, 12. So we have 22 twelfths minus 9 twelfths. So when we do this subtraction, we're going to still be in twelfths. So remember, when you do subtraction of fractions, you or addition, you keep that denominator and you go across on top. 22 minus 9. 13. So if somebody asks you, how many pounds of fish, and you said 13 twelfths, would you expect to be slapped? Maybe, yeah, right. All right, so we probably want this to be in a mixed fraction. That's literally how I think about word problems with fractions, is if you can say the word, the answer out loud and it sounds stupid, then turn it into a mixed fraction. Okay, so 12 goes into 13 once with 1 left over. So that 1 left over is still in the 12th fraction. So we have 1 and 1/12. This was pounds of cat food. That is how much cat food Spider-Man ate this week. That's an entire week of food. Fighting crime does not pay. You are not making an hourly wage. What does Spider-Man make hourly? Nothing. You know, if Spider-Man makes a living taking pictures of himself and selling them, would he have an OnlyFans now?
Yeah,
Now that makes sense.
Okay, there we go. All right.
and the fans would be looking at it.
You're all welcome for that thought. You're all welcome for that thought.
Would Mary Jane be part of it?
What was that?
Would Mary Jane be a part of the OnlyFans?
We're at the point where I no longer want to record this for online. All right. Question, does anybody actually look to see if I uploaded anything?
I haven't.
No?
I haven't, but yeah, I
Okay,
remember
cool.
Last class you told me you uploaded like 2 new ones. And have you uploaded more?
Probably not.
I haven't really used much.
No, his YouTube channel. He has his own YouTube channel. From when he records the class.
Oh, true.
Yeah, that.
So behave in your class.
I only have 2 classes. This is what, the 5th one? All right, well, I'll work in this. That's it, that's it. Hey, look at this.
Oh, it's Robert.
Oh, look at that. Anybody glancing at this might look at
Wow.
this. Teaching it.
Robert, you're famous.
Yeah, Robert.
That's
Crazy.
wow.
That's
That's
what you
why
get for
I
being the only
am.
one that ever
Can I
actually
get an
turned on.
autograph?
I didn't know how to turn off the camera. Oh my god.
Well, you clearly figured it out.
Now.
I'm kind of curious. If I hit stop video, do you guys still see my share?
No,
Yeah.
yeah.
Yeah, you see that? Cool. You should probably have that on. Wonder if I keep like hitting toggle on that, if it'll knock anybody's camera on. Ooh, I can like send you guys notifications to make you turn on your video. Cool, all right. That's okay. That's okay. I know some of you are paying attention. All right. You're actually paying attention more than previous classes I've had, so that's kind of awesome. It's probably because I
Have you
keep rambling, I guess.
Have you lost any students yet?
I'm gonna say no. No, I don't think so.
Well, that's enough, right?
I'm cool with it. Yeah. Yeah, so let's do this. Let's do this. Aquaman is retired to a quaint attraction in SeaWorld. He is fed 4 5/7 buckets of fish every day. Oh, he's a hungry little Aquaman.
Aquaman eats fish.
Yeah, isn't he just friends with them?
Okay, for the record, this is one reason why I don't like Big Bang Theory, because they're not real nerds. Real nerds actually like Aquaman. For the record, when they rebooted Aquaman in the New 52 comics, he walks into a fish restaurant in the first issue, and everybody stops what they're doing and looks directly at him. They're like, "Oh my God, you can't eat this. Aren't you their friends?" And he's like, "No, they're fish. They don't have thoughts. I push them through the water with my mind. I can eat fish all I want." He sat down to eat fish. And then he saved some people, and one of them looked at the other one. "Oh man, my wife's never gonna let me let this down. That Aquaman saved me." It was great. They just leaned into that. All right, so the sea otters are fed 2 1/3 times as much fish as Aquaman. How many buckets of fish are the sea otters fed each day compared to Aquaman? So they're fed this many times that, so you could probably guess that we're going to do multiplication. And we're going to go ahead and improper both of these fun little guys. So 4 times 7 is 28. 28 plus 5 gives us 33 over 7. Over here, we have 2 times 3 is 6 plus 1 is 7 over 3. Now we have a couple options. We can multiply straight across now, or, hey, these are like beautifully set up for cross multiplication or cross cancellation. I mean, so cross canceling, 7 goes into itself once and into this other 7 once. 3 goes into itself once and into 33 11 times. Well, 11 times 1 over 1 times 1, yeah, it's 11.
Does it stay 11?
These two go together very nicely. So we don't have to convert anything. We just get what was it, buckets of fish?
11 buckets of fish.
I'm cool with just writing 11 buckets.
Yeah.
We know what it means. We know what it means. Now that is multiple sea otters for the record. This is just one lazy, hungry Aquaman. He's in SeaWorld. He's in captivity. It's a very small area.
And he's at fast 10.
Hmm?
And he's at fast 10 now.
He's looking kind of chunky in Fast 10.
Yeah.
You know, the fun thing is everybody's like, "Oh my God, they took that little Aquaman, they made him buff for the movies." And like at one point, Aquaman is that big in the comics, has that long hair, but it's blonde. And he also had lost a hand, so he's got a freaking hook. I kind of wish they did that for the movie. Right?
I know, right? I was waiting for Captain Hook to come out.
I'm down for Captain Hook as being a DC superhero. Bring me Batman. All right. So I feel like we're okay with the mixed fractions things. Yeah, kind of. Hey, good enough. All right.
Yeah.
All right. So unit rates. We only got a few examples for that, so I just crammed them on the same slide. Unit rate compares an amount of one thing to a single amount of another thing. So if a tub is filling at a rate of 10 gallons per every 2 minutes, then the unit rate is 5 gallons every 1 minute. So miles per hour is a common unit rate. You know, and usually our unit rates that we tend to use is, you know, either measured in miles per something or dollars per something. You know, what's the cost per ounce? What's the cost per gallon, etc. All right, so number one. Laney bought a set of 20 markers for $6. What is the cost of one marker? All right. Kind of a slow ball here. 20 markers for $6. So we're looking for the cost of a marker. So you can think, okay, I'm probably dividing. Which way do we divide? Do we divide 20 by 6 or 6 by 20? 6 by 20. And the way I like to do that is I like to make like a little, when I'm doing word problems at least, I'll make a little ratio here to show how I'm setting it up. If I'm looking for cost per marker, that's cost on top and markers on bottom. So if I do the cost on top and the markers on bottom, well, we're kind of already done, not really, right? But we're kind of already done. This is the cost per marker. If we reduce that, we got 3/10. Now you could either, since we're talking about dollar amounts, if I threw out a fraction as an answer, it's probably not going to be good enough, right? We're probably going to want a decimal number, right? Well, the nice thing about 3/10 is that, well, it's 3/10. So if I had this as a dollar amount, well, we'd go out 2 digits, 0.30. So it would be 30 cents per marker. So when your kid smashes them, you know how much to yell at them about.
That was too easy.
Well, realistically, you inflate it. It's like a crazy mom whose son sold her PlayStation 3, and then she came into my store and like, this was theft, I'm calling the police. Oh, okay. Do you have anything to show that you own it? It was mine, that's worth $300. It's a PS3, it is now worth $300. It was when I bought it.
When you bought it.
Yeah, that was a decade ago. Through tantrums, figured out she'd have to file a police report against her sister. Came in, I let her buy it back at what we sold it to the kid. Ah, man, she was angry though, it was fun. All right. So if it took 7 hours to mow 4 lawns, at that rate, how many lawns could be mowed in 35 hours? Yeah, and we could kind of do this a couple of different ways.
Is that with sleep or without sleep?
What?
Is that with sleep or without sleep?
Man, I can't hear you. Let me see if I can switch my.
Is it with sleep or without?
With what?
It's with sleep or without sleep?
With sleep?
Or without sleep.
Who sleeps?
I'm just saying, like, you got 24 hours in a day and you're gonna sleep, a little bit.
Some people don't.
That's the Mexican Americans.
That's a good way to put it.
Hey, I'm gonna show you that video Robert sent me about the Mexican American.
Is it bad that I've actually had the thought of I'm having trouble cleaning my room? Maybe I should start doing drugs.
Hey, methingitis is a real thing.
Honestly, I just thought about it. And I was like, it'd be easier for me to just pay somebody to clean my room. I'm just gonna leave it. Yeah. Good luck.
Seriously.
That or I could trade. It's easier to clean somebody else's mess than cleaning your own.
Yeah,
So like, hey, you got a messy room? Cool. I'll clean yours, you clean mine.
done deal.
Yeah. Yup. Yup. All right. So 7 hours for 4 lawns. How many lawns in 35 hours? So the aim here is to do a unit rate. We could do this as a proportion. It would work out either way. But the general idea is, you know, we're kind of trying to figure out how many either hours per lawn or lawns per hour, you know? I would say lawns per hour because we have 35 hours. So we figure out how many lawns per hour you do, multiply it by 35, we're done, right? So if I'm doing lawns per hour, that's how I'm gonna have it set up. So right now, we're gonna worry about getting a unit rate. So we'll do 4 lawns for 7 hours. That is now in lawns per hour. Now, you have a couple of different ways to do this. Since this doesn't reduce, technically, even though I just wrote it down, that's kind of our unit rate already, right? Like that's all you have to do. You do 4/7 of a lawn in an hour, right? So, you know, a little less than 2 hours, you can do it, finish a lawn, right? Well, what I like to do is instead of getting a decimal, we could just multiply that by the 35 hours right now. And the nice thing about this is that if I put this over a 1, we can cross cancel right now, right? If I do that, 7 goes into itself once and into 35 5 times. Well, now my denominator is just 1, so multiplying across, I get 20. And that's how many lawns we can do in 35 hours. Not bad, right? Do I ramble too much? Do we remember what we were doing? Yeah. No, I'm pretty sure I got a worse memory than all of you, so I'm pretty sure that worked out. Okay, that kind of looks like an actual shape. Anybody know what shape that looks like? Gonna do them eventually. No, it's a trapezoid. Okay, how do we feel about unit rates?
All right.
Cool. Let's do proportions. Proportion is 2 ratios equal to each other. Pretty much it. So you can find an unknown value in a proportion using cross multiplication. Remember, you can only use it with one fraction set equal to another fraction. It's the only time you can cross multiply. So let's do some. Oh, I got to the line portion of my notebook. I should really scan stuff and erase it. All right. So Mal's total bill at a restaurant is $34.75, which probably needs a dollar sign on there. There we go. I'm happy now. Bill is $34.75, writing that down. He wants to leave a 20% tip. How much is the tip? Cool. So if you know percentages nicely, there's some pretty easy ways of going about this a little quicker, right? But if you don't, we can always just use a proportion for things like this. So what we can do is set up a proportion where, let's say we have the dollar amount over the percentage. So like the 34.75, you know, if we're leaving 20% of a tip, it'd be 20% of that, right? So we know that, well, what percentage is this already? It's 100%. And then we're looking for 20% of it, so its percentage is going to be down here, but we don't know what the tip is, right? We don't know that amount. So we could put whatever variable you feel like in here, any letter. If you hate yourself, you could draw a little picture of an apple or something. You can use a full word. I don't care. It's a variable. It's a thing we don't know. Default X. Why not? Don't care. Good enough. It's a thing I don't know. So we're going to get Mr. Thing I don't know alone. So we're going to multiply this to that, and that'll be equal to this to that. That part's easy. 100x equals whatever 20 times that is. I don't know. Where are you, Mr. Calculator? You're going to calculate. 34.75 times 20. 695. Cool. And now to get the x alone, since it's multiplied onto that 100, we're going to divide off that 100. And the nice thing about dividing by 100 is it just moves the decimal point over twice. So we would be at 6.95. So that would be the dollar amount of our tip. If you needed the total, you could just add them together. If there was a sales tax amount, you could do the same thing with this and then figure out the sales tax amount there. It'll work. Now, once you get good at percentages, you can just do 34.75 and multiply it by 0.2. And there we go. A little easier, but we'll get there. Let's do more. I love these. I'm so excited about these. So we have Maddie is carrying a 5-liter jug that weighs 7.5 kilograms. He wants to know how many kilograms a 2-liter jug of sports drink would weigh. He assumes the relationship between volume and weight is proportional. What is the weight of the 2-liter jug? Okay. So, some basic notes for that. 5 liters is 7.5 kilograms and 2 liters is, I don't know, kilograms. This is 100% how I do my own math, by the way. Every time I do a word problem, I'll write out what actually matters and how they relate to each other. I know I'm doing a proportion for this problem, so I know that I'm going to be setting it up kind of like that. Now, since we're just looking for a simple answer, we're not looking for a unit rate or anything, it's not going to matter how we set up our proportion. We could do kilograms over liters or liters over kilograms. It really doesn't matter. Not even a little bit. Because if you have a fraction equal to another fraction and flip them both upside down, it's still going to work out the same. So it does not even matter how I set this up. As long as I keep it straight, right? So I know that I have 5 liters is 7.5 kilograms. That's gonna be set equal to 2 liters over, I don't know, kilograms. I don't know, let's call it a K. I don't know. Why not? You can call it whatever you want. Draw a picture of a pickle if you want to. Please don't start drawing pickles on your books. All right. So K times 5 is 5K. 7.5 times 2 is 15. And then to get the K alone, we're going to divide off this 5 because it's multiplied onto the K. So we get 15 divided by 5, 3. And I put it as a K to remember, hey, this is the kilograms part. So that's its unit. You can always pick your variable based on that. That's one nice way of doing it. That way you get to the end and you're not left like, wait, what does this mean? I got this thing equals that, but what is this telling me? That is a common problem with the word problems. Random stray marks from the last time I used this page. All right. Here we have somebody with a problem. Says Mika can eat 21 hot dogs in 15 minutes. She wants to know how many minutes it would take her to eat 35 hot dogs if she can keep up the same pace. That's a problem. You should talk to someone. All right. That is a lot of hot dogs. I hope they're at least Nathan's and not like, Bar S or something.
Wiener Schnitzel is amazing.
See, I'm down for that.
Gotta go to Reno.
Yeah. Well, if you couldn't tell, I walked here, so getting the Wiener Schnitzel would, honestly, yeah, I could probably get away with eating 35 hot dogs and a Wiener Schnitzel and walking back.
Definitely worth the trip.
I go to Reno, I'm going to either Popeyes or Juicy's. Could go for some. I want some spicy strips, man. Some spicy strip.
The gumbo at Popeyes is amazing.
I haven't been there in years. I didn't know they had gumbo. I'm down. I will not dip my freaking chicken strips in gumbo. I'm down. All right. So we got 21 hot dogs is 15 minutes. 35 hot dogs is, I don't know, minutes. Let's do hot dogs over minutes because I'm kind of curious what the unit rate would be because that's messed up. So 21 over 15 would equal 35 over, I don't know, minutes, M for minutes. If I did a unit rate, be 21 divided by 15, that is a 7. That is a 7. You ever notice that phones and calculators have the numbers upside down from each other? I have no idea why. You need 1.4 hot dogs per minute. I feel like you could do better than that. I guess it depends on the hot dogs. All right, so cross multiplication. M times 21, love that multiplication. This is why sometimes algebra is easier than just basic math, because what happens if you multiply a number times a variable? It just kind of sits next to it. Less effort. 15 times 35. I don't know, 525. All right, so we're going to divide both sides by that 21 to get the M alone. And we get whatever 525 divided by 21 is. Apparently goes in even, we get a 25. I pass judgment on this person unless they are wrapped in bacon. All right. I'm hungry. I haven't eaten today. All right.
Apparently hot dogs are really good.
So good that you could eat 35 of them in 25 minutes.
That's horrible.
Yeah. All right. Let's do more math. I love math. Don't you guys love math? Yeah, you do. Yeah, you do. You do. You do. Yeah. Cool. All right, factor trees. They're trees. You use them to factor. Yeah. That's what it is. So if you don't recall, you take a factor number, split it in two different branches and say, yeah, these two things multiply to that number. Does it have to be the smallest thing that goes into there? No, could be anything. Could be, in this case, 48 is 8 times 6, could have done 2 times 24, doesn't matter. Then you just keep splitting them down all the way until you have nothing but prime factors left. And remember, prime factors are divisible only by 1 and themselves. So basically, they're just numbers you can't split further down, right? So factor trees are a thing. Let's do some. I love it. You love it. We all love it. That cat doesn't love it. Accurate picture of my childhood. Accurate picture of my adulthood. All right. Somebody asked me, hey, what do you do for fun? I'm like, hide from the world. You've been out there in the world, there are people there. I've met a lot of those. I'm kind of done. All right, so 250. What goes into that? Well, the way I like to do it is if it ends in a 0, I always like to split that off. 10 and 25. All right. 10 is 2 times 5. 25 is 5 times 5. So the prime factorization of this guy, because everything's done, is 2 times 5 times 5 times 5. Remember, you always want the bottom of every branch. You don't want to, like, if you have kind of a mess going on, you got to be careful to keep the bottom of every branch, right? All right. $250 was too easy. Let's do 48,510. Because. All right, so that's 0 at the end. So it's going to be 10 times the other digits, 4851. First thing I notice, it ends in an odd number. Doesn't end with an even number, which means we can't put any even numbers into this guy. It's not divisible by 2 and it never will be. So we're going to start throwing other numbers at it. You don't know? I don't know. Let's try dividing it by 3. Let's see what happens. 1,617. Cool. Well, let's see what happens if I divide that by 3. 539. All right. Let's keep it going until we can't anymore. Well, that was it. So I tried to divide it by 3. I get a weird decimal, means 3 doesn't go in evenly. So, wow, I wrote that like an idiot. All right. 3, 539, like that, not like I had before. Just remember, your math teacher is an idiot. If you see me do something stupid, correct me. All right. So we have 539. Doesn't end with an even number, doesn't end with a 0 or a 5, so things we can rule out. 2, 3, 5. Let's try 7. 7 times 77. All right, don't need that anymore. 77.
11.
No way. How'd you pull that off?
You did most of the work.
Okay, that's fair. All right.
I can do the next one.
I don't remember what the next one is. I wrote
2
it.
times 5.
Okay. I was gonna ask if we were done and if anybody sees something we didn't do, but fine. All right. So
Now we're done.
now we're done. We have 2. We got 2. I like to put them in order. 2 3s. A 5, 2 7s, and an 11. How exciting. No. And any way you factor tree this thing, if you had done 2 up here, you would have gotten, I don't know, whatever 5 times that thing is. Yeah, it doesn't matter how you go about it, you will always end up with the same prime factors. So it's very, like, the important thing I want to go to push on you guys with this is that, hey, however you do it, as long as your math actually checks out, you're good. Okay, number 3, demonstrate that the prime factorization of 126 is the same as the combined factors of both 14 and 9. All right. Well, first thing, let's just break this guy down. That was fun. We got 2 times 63 turns into 3 times 21, which turns into 3 times 7. So 2, 3, 3, and 7. Is that what we get if we play around with everything over here? Well, yeah. Because if I multiply these 2 numbers together, it will equal 126. And I know that already because these guys are the same numbers here. So they'll multiply out nicely. Oh. Oh. You need to reset your Wi-Fi router. All right, we'll hit it with a hammer. I hate resetting my my router. It's annoying as hell. Obviously, I'm the nerd that set up my home internet for my parents. I literally just bought it
Setting
out.
that stuff up is fun.
What? I didn't hear you. My ears were off. Yeah, no, I 100% just buy a router, set it up already, and then if they have to like play around with the service or anything, I literally just tell the guy to plug in that router. Just plug it in, everything will keep working fine. Just tell them to plug it in. That's all you have to do. Everything's already set up. I see you writing. I'll wait. You got this. Are you done writing? You got this? Okay. Cool. All right, how do we feel about, well, everything? How do we feel about everything, all of this? We good, we happy with it? You see what we're gonna do with some factor trees? Now that they're not problems, they're just gonna be a part of everyday life. Cool. Hey, look, greatest common factor. So greatest common factor, or GCF, it's the largest factor that two or more numbers have in common. As a check, both numbers are perfectly divisible by the GCF. For example, if you have 10, 20, 30, 40, 50, and 60, what goes into all of them? 10, right? They're all divisible by 10. Cool, then that's the greatest common factor. And it can't be any bigger than 10 because the smallest number we have is 10. I can't say 20 goes into 10, right? It would go in 1/2 times. That wouldn't work. So let's see. Yeah, so far we have used greatest common factor essentially in simplifying fractions, right? You look at your fraction, you say, oh, this will reduce, okay, by what? You start chopping it down, right? And that's literally a great usage for greatest common factor. Okay. Later, greatest common factor is especially useful in factoring larger expressions in algebraic functions. It's extremely useful in cleaning up large problems. It really is. It just, if I didn't have that, anything higher than like basic algebra, just take all day. Okay, so as I discussed before we started, there's many ways of finding your greatest common factor, but this is the simplest way I could find to put it on paper that you guys could maybe see. So first off, you start off by listing the prime factorization of all your numbers involved. You'd find it by a factor tree, right? And you would select all the factors that are common to all the numbers. So for example, we have 15, 30, 45, and 90. There we go, we have it laid out. Now there is, you could technically pull it off from here. But if you're not seeing quite how that makes sense, this is the method to kind of go with. So what you do, I'm going to rewrite this a little bit. Oh, I regret doing that. So line them up with each instance of the factors getting columns to themselves, subsequent numbers using that same column first, then adding a new column when a factor is repeated. So that's kind of an awkward thing to focus on, but the general idea is, hey, you write out your first number, cool, it's 3 times 5. Then you go to the next one, well, 30 was 2 times 3 times 5. We already have a column for a 3 and we already have a column for a 5. So you put the 3 and 5 there, and just since you still have that 2 left over, it gets a new column. So it's still 2 times 3 times 5, just we're filling in those columns as we go. 45 was 3 times 3 times 5. Well, we had a column for 3, we had a column for 5, but we don't have a column for a second 3. So we make a new one over here. So it's still 3 times 3 times 5, just kind of spread out. And then 90 was 2 times 3 times 3 times 5. So we actually had a column for each of those. The 3, the 5, the 2, and the second, right? So you get them all lined up, and kind of every time you have that factor already in a column, you drop it into that first column. You move on, you have that factor in a column, cool, you drop it in. you're kind of working left to right. We didn't have a 2, but we had an extra 3, so you start a new one. Same down here, 90. We had a column for 3, had one for 5, had one for 2, and had one for that 3. So you kind of work it down that way. Then your greatest common factor, there we go. Your greatest common factor is all of the columns that are common to all of your numbers. Well, they all had that 3 and they all had that 5, right? So that is your greatest common factor, is that 3 times 5, 15. So that's telling us that every one of these numbers was divisible by 15 and nothing larger than that. So it's a funky way of doing it, but it works. Even if you don't fully understand the method, as long as you can pull off putting the things in these columns, it will work out. Now, of course, like I said, that's not the way that I usually do it personally. This is the nicest way I could find to put it on paper. So what we're going to do is, as we're going through this, I'll be doing this method, then I'll show you how I would normally do it. And we're going to kind of slowly, whenever we need to use these concepts throughout the class, just pivot to the quicker method. So the idea right now is getting it to click, understanding what a greatest common factor is. After that, we're going to find a nice way to do it. You know what? I don't like this. I don't like this tile at all, this slide at all. I don't care. Let's just kill it. Cool, let's do some. I like it.
Yeah.
You're all gonna like it. You're all gonna like it. All right. Number 1, we got 15, 30, and 105, and you probably guess what it is. Nobody's gonna try. All right, whatever.
15.
Yeah, you're right. It's not like I just took the example off of the slides and just changed one number and dropped one.
No, not at all.
Not at all. All right, so whatever. We're looking for the concept, right? And this, we've already kind of seen this one pretty much in action. So let's work it out. So we need the common, or the factor trees for everything right away. Three times 35, 5 times 7. Okay. And yes, I did do those in order intentionally, otherwise I would have just done 5 times whatever, and I would have gotten 21 and still would have gotten 3, 5, and 7, whatever. So what you want to do, I want to try it a little differently than I usually do it. Usually I start off and I list it from the smallest number down. I'm going to try from the largest number down. Let's see what happens. See if it makes the column thing easier. So what we're going to do, we just list them out like that. And then the first number, we're going to write out its factors. And we're going to give a little bit of a gap so we can tell that it's in a column, right? 3 times 5 times 7. Cool. Now 30 is 2 times 3 times 5. So remember, we kind of think of them as slotting into these columns. We have 2, 3, and 5. Well, we have a column for the 3. We have a column for the 5. We don't have a column for the 2 yet, right? So we're going to go ahead and make one. And then 15 is just 3 and 5. do not know what your direct messages mean. I'm going to keep talking. Yeah, no, I have no idea. Cool. All right. Oh, your keyboard's angry. Okay. Get you a new keyboard, jeez. Are you on like an angry laptop or something? For those confused, I'm not responding to the direct message. I could type, I guess. That'd probably be the normal way to do it.
It's too much work.
Yeah, that's true. Oh, locked up? Okay, well, you know, hit it with a hammer. For those uninitiated, do not ever, I did not confirm that it was a laptop, but I was talking about laptops. If you ever have a laptop that you want to destroy, do not hit it with a hammer. There is a battery inside. If you start messing with it, it will explode.
One is.
Which is why you hit it with the hammer.
You don't
Hello.
want to be that close to it if you hit it with a hammer. Now, if you're, yeah, you can
You
throw
get a
it.
sledgehammer.
Yeah, but that sucker is, I mean, if you remember years ago when there was one of the Samsung phones was not allowed on planes because it was spontaneously bursting into flames. And they had to.
I remember that.
Yeah, they had to basically recall the whole thing and kill the product line. That was
hilarious.
the battery incorrectly. And yeah, they actually, every single one of the phones they shipped was in fact a little explosive. Oops. So, you know. Yeah, don't mess with lithium ion batteries. Get a bucket of sand, throw them in there. If your phone looks like the back of it is bulging off, take it immediately to a repair center. My mom's laptop keyboard was actually like popping upwards and the little touchpad was starting to sink in. And I was like, what have you done? Did you bend it in half or something? It turned out that the battery was twice its size. It was expanding and it was ready to blow. Cool, all right. Replace that battery for 20 bucks, everything's good as new. All right, so the columns are filled out under the, wow, I almost wrote another 3 under that 5. Columns are filled out under the 3 and 5. So we get our greatest common factor being both of those, so 15. It's always only whatever has the columns filled out.
So we don't use the 7 and 2.
Nope. There's only a 7 there, there's only a 2 there, so it's not common to anything. Now, one way that you could do it, the easier way that I talked about, is that you could look at your factor trees and say, anytime you have a factor in common, give it a circle.
Mhm.
Give those a circle. And you can see that 3 times 5 pretty quickly. Now,
Right.
this is very easy to understand and look at for greatest common factor. But when we get to least common multiple, the factor tree method's a little harder to understand. And the reason that I've picked this method to go over is because this method will work for both of those concepts. So I'm kind of giving it to you here. This method's going to be quicker and easier, but you can visually see it quite nicely here too, right? So either way, you will end up getting that 15. Like I said, I'm going to do it both ways on every single one of these problems so you can kind of see it.
Okay.
All right, so number 2, we have 12, 30, 17, and 180. Little harder to eyeball, yeah? It's a little harder to eyeball because it's kind of a trick question, but whatever. All right. So factor everything as far as it'll go. 12 is 2 times 6, which is 2 times 3. 30 is 2 times 15, which is 3 times 5. 17 is, well, what goes into 17? I don't know, nothing, right? I'm just gonna, so we don't forget about it. Yeah, there's a line, 17. That's already prime, right? And then 180. We get 2 times 90. Which is 2 times 45, which is 3 times 15, which is 3 times 5. All right. So just like last time, I'm going to go ahead and write these out in order of largest to smallest. Still haven't decided if I like this way better, but you know. What you can gather from that concept is that it doesn't actually matter what the order is here. Just that you keep everything straight. The reason I'm trying it out with the larger number on top is so that I have columns for as many factors as I can to start off with. So 180 is 2 times 2 times 3 times 3 times 5. Who? All right. $30 was 2 times 3 times 5. So that 2 is going to go into the first column of 2s. That 3 is going to go into the first column of 3s. And the 5 will go into the 5 column. Now, we haven't run into it quite yet, but whenever you have multiple of that factor, put it in the first column that it hits. Because otherwise it could get kind of screwy. You might put a 2 here, you might put a 2 here, you might put a 2 here, and then you wouldn't see that it works out, right? 17. 17 is just 17. Gets its own column. And 12 is 2 times 2 times 3. Greatest common factor is, we don't have one, right? That 17 broke everything.
Yeah.
We don't have one. Now, for this particular problem, we're going to revisit it when we cover least common multiple. So I'm going to leave a little bit of an extra line here, and we're going to move on, because this problem might not have a greatest common factor, but it will have a least common multiple. So
I have a quick question.
I have a quick answer.
So far with the greatest common factor, the greatest common factor for all of them has been the smallest number that is in the bunch of numbers. So couldn't you just say that the greatest common factor in the group of numbers is the smallest number of that group?
Not necessarily, because, well, if you think about it, if I didn't have that 17, I just had these columns, they still wouldn't have that second 2 in common. So it would have been a 2 and a 3. So it would have been 6 between 180, 30, and 12. It wouldn't have been 12. 12 doesn't go into 30. So you can't just make the assumption it's going to be the smallest of the numbers, because in this case, even without that 17 breaking stuff, it wouldn't have worked.
Gotcha.
Let's do another. Okay, so the next one is 24, 168, and 40. Kind of a funky looking one, probably like 4 or something, right? But let's see what we got. So we break things down as far as they go. 24 is a bunch of 2s and a 3. 168, I don't know, but it's even, so 2 goes into there 84 times. 2 goes into that 42 times. 2 goes into that 21 times. And that's a 3 and a 7. And then 40. That one's 10 times 4. So we have a 2 and a 5, and a 2 and a 2. So a bunch of 2s and a 5.
I have another question.
I have another answer.
So 17 didn't have a greatest common factor, right? So is that all odd numbers except for 5 that don't have a greatest common factor?
No. So looking back at this, the reason it didn't have a greatest common factor is not because it had a 17, but because they all didn't have a 17. This one, the 17 wasn't, like if it was maybe like a 34, I would have had a 2 right here, and it would have been just 2. It just happens to work out that way that 17 was our wrench breaking stuff. But it could have been that every single one of these could have been divisible by 17, and then we would have had 17 as the greatest common factor.
Okay, so it doesn't matter if it's an odd number or.
Nope.
Okay,
It doesn't matter anything. It has nothing to do with what the numbers are, and it's literally only if they're in common with all of our numbers here.
gotcha.
Its name is what it is we're looking for, greatest common factor. We are looking for the greatest factor that is in common with all of our numbers. So again, I'm going to go ahead and write these down in order from largest to smallest. 168, 2, 2, 2, 3, 7. 40 was 3 2s and a 5. 2, 2, 2, 5. Don't have a column for that 5 yet, so made one. 24, we have 3 2s and a 3. 2, 2, 2, 3. So the odd ones out on this one are that 7 and that 5, right? But even that 3 isn't, that 40 isn't divisible by 3. So when we're looking for our greatest common factor, it's only the columns that they all have in common. Because those are numbers. That 8, every single one of these is divisible by an 8, but nothing larger than that. And again, like that last one we had a common factor on, you could go through and say, okay, we have a 2. We have another 2. We have another 2. And then this one has a 3, this one's 3 and 7, this one's 5. They don't have anything in common past that. So you do that multiplication and you get the 8. That will work out for these numbers as well. Okay. How do we feel about this method? Is it confusing, weird, funky, doable? Doable? Kind of rough, but doable.
I think it's doable.
Okay. Let's go ahead and move on from these particular problems. Let's look at these fractions over here. So find the greatest common factor and simplify. So what I'm shooting for here is to be able to reduce these numbers by larger numbers than we're used to. Now, yeah, we might be able to look at this and say, oh, well, that's going to be a 6, right? But if you can't see that, or if you have, you know, maybe it was 40 over 168, you would have to actually break them down a little bit. So let's just go ahead and do the factor tree method on this one and skip that column table. So we get our factor trees. And then whatever they have in common, we find it, all right. So we find the greatest common factor, which in this case is a 6. And the instructions say, find the greatest common factor and simplify. So the idea is, now that we know it's 6, you could say, oh, 6 goes into here twice, and 6 goes into here 5 times, right? So this thing breaks down to a 2/5. Now, yes, you might be able to do that a little quicker, being able to see that 6 goes into both of them. But again, this concept scales up. So if it has significantly uglier numbers, this method will work. No exceptions every time.
Can you show us?
Man.
Just one.
Okay, well, I'll skip
Super ugly.
I'll skip to number 8 because number 8 is 196 over 462. And I picked those numbers specifically because we number 4 actually covers those numbers and we would have already been familiar with them, but we skipped that one. So it's fresh. 196 over 462. Let's do it. So we need a factor tree for both. Both of them are all kinds of I don't know, right? But they're both even. So I can divide that by 2. I get a 98, which is still even. So I could divide that by 2. I get a 49. Oh, nice. That one's 7 times 7. 462. Divide that by 2, we get 231. I have no idea what goes into 231, but I know it's not going to be a 2. It's not going to be a 5. Could be a 3. Let's try 3. 231 divided by 3. 77. So we have 7 and 11 there. Okay. So what's in common? Let's circle what we have in common. This one had a 2, that one had a 2. This one has a 7, that one has a 7. Now what do we have left? 2 and 7, 3 and 11. Cool, that's it, right? So we know that we have a 2 and a 7 coming out. So 14 would be the greatest common factor. That's not something I'd be able to eyeball, right? 196 over 462. Oh, obviously those are divisible by 14. No. I'm okay at math. I'm not that good, right? So what we're gonna do. So we have 196 over 462, and now we have to say how many times 14 goes into that, which is a heck of a lot easier than you probably think it is. Is how many times does 14 go into 196? You know, it's fun. Go back to your factor tree. Say, hey, if I pull those out, what factors do I have left? 2 and 7? That'd be 14. All right, what about 462? How many times does 14 go into that? Well, if I pull out that 14, what do I have left? 3 and 11? How about 33? Because 2 times 7 times 3 times 11 is 462. If I'm reducing both of these by a 2 and a 7, those things are going to disappear, but the other factors are still going to be there. And if those factors are still going to be there, then I can make use of that concept by saying that's what it reduces to. Another way to look at that. Huh? Go ahead.
Because it's its other half.
Yeah, exactly. You could think of it as almost, since I would have this factor tree divided by this factor tree, these two 2s are canceling off and these 7s are canceling off. You could see it that way too. And then you would just have these left over on top and on bottom. Now you could always go the tried and true way of, hey, 462, what is that divided by 14? 33. Just reduce that way too. That's an option. How do we feel about greatest common factor?
You like even numbers.
Even numbers are nice, lots of 2s. I didn't really want to give examples of gigantic prime numbers, and I'm not going to lie, the likelihood of you running into them pretty low. So
That's good enough.
yeah. Yeah, this is the idea. Okay. We like it.
Good.
Okay, cool, because you get to do it now. So I know they're not everybody's favorites, so what I'm going to do is let's not do number 10. Is there a strike through option here? Oh my God, are you serious? This is a very basic thing in every word processor I've ever used in my life. There's not a strike through. No, okay, whatever, fine. Fine, Google Slides. Be as basic as possible. Okay, so everybody start working on these guys. We're gonna go ahead and skip number 10. So do number 9, 11, and 12. 9, 11, all right.
Wow.
I'm sorry, it's a terrible joke. Said you'd never forget. You know what I never forget? Freedom fries. That was a thing. We don't want French fries. We don't like the French. We're gonna call them freedom fries. All right. Weird. All right, I'll try to shut up for about 10-ish minutes. If you have questions, as usual, ask them. Yeah, absolutely.
We were just doing that.
9, 11, and 12. All right, so how did we do?
Or
Horrible?
Dog shit,
Huh?
dog shit.
Don't do that. All right. Those of you online, how'd you do? Any ideas on some of these? Ooh, okay. All right, so I see it went well. All right. They're all gonna be very annoyed with how basic the answers are. Let's see, we had 12, 26, and 40. So. Okay, we're gonna break every one of these down as far as we can go. So 12 is 2 times 6, which is 2 times 3. 26 is 2 times 13. And 40 is 4 times 10, which is 2 times 2. And 2 times 5. Just looking at that, what do they all have in common? 2, right? Nothing else, right? That one having a 13, there's no 13s anywhere else. That means the greatest common factor for this problem is just 2. Now, of course, if you do it the longer way, it does look a bit different. 40 is 2, 2, 2, and 5. 12, 26, I mean, is 2 and a 13. And 12 is 2, 2, and a 3. At which point
Is the school,
what? Oh my God.
the sharing? Yeah. I don't see anything.
You don't see anything?
Except for my name draped across the computer.
Everybody online, you seeing stuff? Hello? I got a yes. Okay. Let's try, I'm gonna try to stop the share and then go back to it.
Oh, got it.
Well, now I broke it.
I found it.
Alright.
I'm illiterate. Sorry, that was me. I don't know what happened.
Dude, this is Nevada. Most people are illiterate.
It's the water.
I think so. It's the cancer water. I don't come near, I don't like, you know. I use the tap water to clean. I feel bad about it. I'd rather use like bottled water to clean my dishes around here. Like that is, oh. We got cancer water. Okay. If you do it this way, you still end up seeing that the 2 is the only thing they all have in common.
I would have,
Huh?
I would have been right answer, but I'm worried about multiplying them all together.
See, that's the thing. You don't want to multiply them all together because you know what they are multiplied.
Yeah.
That's actually a really common thing I see with math is people kind of following the method and then undoing it at the very end.
Yeah.
Because you see all these numbers and you see that they multiply together. So the thing that you think of is, well, I have multiplication symbols, so I multiply, right? But you just got to keep in mind what it is you're aiming for. What's your goal? Your goal is to see what they all have in common. Okay. Any questions on number 9? So did we have fun with the fraction ones?
No.
Okay, so the fraction ones was find the greatest common factor between the numerator and the denominator and use it to simplify.
But they did get a bunch of 2s.
Huh?
I did get a bunch of 2s.
Oh yeah, there's tons of 2s in this thing. Tons of 2s. All right, so let's go ahead and factor tree them. 16 and 48. It's 2 times 8. It's 2 times 4, which is 2 times 2. So we got 4 2s there, then 48. 2 times 24, 2 and 12, 2 and 6, 2 and 3. 2's everywhere, right? let's skip the grid method. Let's just look at these as, hey, what do they have in common? 2, 2, 2,
So the answer is 2.
and 2. Well, we're looking for what the greatest common factor is. So our greatest common factor is the fact that we just circled 4 2s, right?
Yeah.
So we multiply those together and we say, hey, what is that? Well, 16 makes sense because it was every factor out of our 16, right?
Yeah.
So that tells us that this is reducible by 16. Now, it's a little tricky to look at this and say, oh, that thing where he said just write what's left.
16.
Kind of tricky, right, on that one, because yeah, if I got rid of all these 2s, what do I have left? Well, with the 16, well, how many times does 16 go into 16? Once. So how many times does it go into 48?
2.
Hmm,
Wait.
3. Cool. So we end up with 1/3. So we're looking for the greatest common factor and the simplified fraction. Now, if you ever want to make a future math teacher hate their life, you could absolutely get away with, and this isn't a shortcut, this is a long cut. But I can make sense of this sort of thing. You can look at this and say, oh, I don't know what the biggest thing that goes into there is, but I know 2 does. I don't know what the biggest thing that goes into there is, but 2. And 2. Oh, how many times does 2 go into 2? Not 2.
1.
Yeah. Yeah. So like that'll work to simplify a fraction. And then you can keep in mind what it is you put in there. You put a 2 in there, you put a 2 in there, you put a 2 in there, you put a 2 in there. Hey, guess what? Multiply all those together. That was our greatest common factor. We use our greatest common factor because instead of 1 step for each factor, we do 1 step. So that's essentially what you're doing is you're making sure that you don't have to do this many steps by being able to reduce by a larger number. So you're on a test, cough, cough. That is essentially what it is you're doing. Worst case scenario, it'll work. Number 12. We had 28/84. Oh boy, I wonder what the answer is on this one. That's 2 and 14, which is 2 and 7. It's 2 and 42, which is 2 and 21, which is 3 and 7. What do they have in common?
2.
2, another 2, and the 7. 2 times 2 is 4, times 7 is, well, what was it here? 28? So that's our greatest common factor. So what does this break down to? Well, 28 goes into itself once, right? How many times does 28 go to 84? 3 right there that we didn't quite hit. It's the only factor it has left, so it's the only thing that goes in. So we have 1/3 again. Did I do that intentionally? Oh, you betcha. I regret nothing. It's like when I remember in differential equations class, giant horrifying math problems, might take like a page and a half of math, get all the way to the end, equals 1. It's like it just made you mad. That's all it did, equals 1. Like, are you kidding me? Do you know how much I went into this? Okay. That's greatest common factor. Do we hate it? Do we like it? Kind of see it?
Trying to see it.
Kind of see it. I'll take kind of.
Sorry.
Sorry. All right. So, yeah, let's do more stuff. You guys love math, right? We have another half hour. It's okay, we skipped the first 15 minutes, it's cool. I was dying. Hey, you know what I like? Walking downhill, not uphill. And not being in a hurry. All right,
My
what?
my son goes to Eagle Valley and they have these big ass hills, right? And
Yeah.
so while I'm waiting for them to get out of class, I used to roll down the hill just for the fun of it.
Oh, what?
And I got told I can't do that no more.
You're not allowed to roll down the hill?
Yeah,
What the hell?
that's what I said. I used to do it all the time as a kid, but I guess as an adult you can't do it.
I do it anyway. What are they gonna do? Call cops? Yeah, he's rolling down the hill. Cops will look at him, so?
They caught me rolling dirty.
Oh my God. I'm not okay with this. All right, so. More stuff, least common multiple. So we just found how to find the largest common factor between 2 or more numbers. On the other hand, this is kind of the other way around. We are finding the least common multiple between 2 or more numbers. So it's kind of like lowest common denominator, right? Where we are finding the smallest thing that both numbers go into. Same idea here. We have multiples of our numbers. We're looking for the smallest one they have in common. Well, there's a lot of ways you could look at that. You could list out the multiples and then say, oh, okay, well, if I do multiples of 2 and multiples of 3, first one they have in common is 6. There we go. But the nicer way to do it is to actually have something to work with, right? Well, guess what we're gonna do? Yeah, same thing. So literally the only difference is the last step. And yes, I use the exact same numbers to illustrate this. So same thing. Line them up, do the column thing. Add a new column anytime a factor gets repeated, you don't have a column for it. Exact same thing. The only difference for finding the least common multiple, because greatest common factor, what is it? Well, it's the biggest factor that fits into all of them, right? But now we're looking for the smallest thing that they all can fit in. So instead of picking what they have in column, we actually take one thing from every single one of these columns. So the only difference is the fact that this thing is going to be, kind of like how the last one was no bigger than the smallest number we had. This one is going to be no smaller than the largest number we have. Because, hey, we know 15 goes into 90. What's the smallest thing that both 15 and 90 can go into? Well, it'd be 90. What's the smallest thing that 30 and 45 can go into? Well, 30 times 3 is 90 and 45 times 2 is 90, so 90. So the idea is that this all comes down to just their prime factors and being able to see what we could do with them. So I got a bunch of examples, of course. This is incredibly accurate. I took this picture and sent this meme to a coworker who is desperately telling people that I'm helping her with math, and I have met with her twice. And she kind of needs to buckle down and do it more. Before we move on and start doing these problems, a little problem that had that weird 17 hanging out in it. You know what our least common multiple on these ones would be? 2 times 2 times 3 times 3 times 5 times 17. $3,060.
That's the answer.
If I did the least common multiple between 12, 30, 17, and 180. 3,060, because it's one thing from every single column. What's the first time that 180 and 17 have a multiple in common? Well, since 17 doesn't go into 180, it's going to be a while, right? So that's the idea with least common multiple. You might have no greatest common factor, but between two numbers, you're always going to have a least common multiple. See, it's a good example. I like it. Looked like a major trick question until it isn't. Like to say I planned it that way, but it actually kind of fell into place when I was teaching the previous class. I was like, hey, let's go back to some of these, because if we go back to them, it's the same math. So some of these we don't really have to stress about, right? Find the least common multiple between 4 and 5. Well, what's the smallest number that both 4 and 5 could fit into?
4 and 5.
Yeah, number 1, we have 4 and 5. The smallest number they could both go into.
20.
Oh, yeah. Right.
Yeah, 5 doesn't fit into 2.
Oh, sure.
Well, so it's 20, right?
It is
Yeah.
20, yes. Because
Okay.
if you start multiplying out 5, 10, 15, 20, 25, 30, etc. What's the first time that 4 can actually fit into one? 20, right? So that's the smallest number that both of those go into. That is the least common of their multiples. That's literally what it's called. 14 and 21, little trickier, right? But 14 is 2 and 7, and 21 is 3 and 7. So 2, 3, and 7. 7 would be the greatest common factor. This is the other way around. Yeah, so these ones are a little funkier to see on a factor tree. So first of all, I'll do it with our chart, so you can see what's happening. So 21, we have 3 and 7. 14, we have 7 and 2. Don't have a column for 2, so there we go. Now we can easily see what our greatest common factor is, right? Because both of these are multiples of 7. So obviously greatest common factor would have been 7. But what's our LCM? One thing from every single column. We end up with 42. Because 14 times 3 is 42. 21 times 2 is 42. So if I had a fraction where I needed to add, something over 14 and something over 21 together, I would know that the smallest thing I could get the bottoms into would be 42. And that's what I'd be aiming for. Anything higher than that, and I would have something larger than I need to, end up doing a lot of reduction later.
And it's always gonna be one from each column, right?
Yep. Now, like I said, there's multiple ways to do these. The greatest common factor was really easy to see on the factor trees, because then we could just circle it and be like, yeah, absolutely there. So the way that least common multiple works is you need at least as many of a factor as the largest amount of factors that one, well, like the largest amount of that factor that any of our numbers has. So if I look at this and I decided to do it with the factor trees, I would say, okay, and usually work my way up from the smallest number to the largest. 2s. What's the most amount of 2s that any of these have? This one has 1, this one has none. I need the 1. 3s. What's the largest amount of 3s that either of these has? None, 1. So I need 1. 7. What's the largest amount that either of these has? This has 1, this has 1. So I need 1. If I do it that way, it will work out every time. But I have had students literally break into tears trying to teach them this. Some people, it just doesn't click on. So that's the reason why I use this method to explain it, because you might not be able to see that, it might not click, but if I start breaking everything into columns and say, just take one thing from every column, it'll work. Yeah. Okay. Number 3, we have 24, 11, and 14. Now, right away, I can tell that it's going to be a large number because we have 11 in here, and 11 is a prime number. So it's going to be essentially whatever these two work out to have, and then an 11 tacked on. So let's go ahead and do our factor trees. There we go. Don't die. Dying's bad for you. At least I think so. Haven't experienced it yet. I don't know. We'll see what deity comes up and says, dude, you're weird. Oh, what have you been doing with your life? Why do you keep taking crappy jobs so you could still teach math and make nothing from either one? Yeah, whatever. Because I like my hobby job. All right, 14, that's 2 and 7. So we have a column for 2 already. We don't have a column for 7, so there we go. And 11, well, guess what? We don't have a column for 11. So if I was to look at these and say, hey, what's my greatest common factor? They have nothing in common, right? Like even just between the 24 and the 14, it would be 2. Now, if I'm looking for the least common multiple, like I said, one thing from every column. All right. let's see what we got.
I think it's only two.
Cause that one has 3 2s.
Oh, okay.
This is basically 24 times 77. So we end up with 1,848. You can see that, well, you might be able to fall into the greatest common factor, or depending on what you're using it for, like fractions. You know, like you might be able to just kind of like trip through it by breaking things down step by step by step. If I was specifically using least common multiple with some funky numbers, it might take a while to fall into that. Now, conceptually, same thing with the factor tree idea. Again, if I started from the smallest factor I have, worked my way up and said, hey, how many of these is the largest amount from any of our numbers? If I started with 2 and I said, oh, there's 3 2s here and there's 1 2 here, I would say, okay, 3 is bigger, so I need 3 2s. Okay, and then the next number would be a 3, none, none, 1. Next number would be 7, none, none, 7. Next number would be 11, none, 1, none. And I get the exact same line here as I do up there. Now, again, if you understand it this way, this is going to be quicker, obviously, but it's harder to understand. So usually I say stick with this until it clicks. When it clicks, you usually have a good way of skipping doing this chart thing. Let's do more. 15, 10, and 4. Okay, so we're looking for the least common multiple. Now let's do the factor tree method first. Smallest factor we have is a 2. So there's no 2s, there's 1 2, there's 2 2s. So we go with the larger of that, 2 2s. Next number is 3, 1, none, none. Take the 1. Next number is 5, 1, 1, none. We would need a 5. Multiply those together and we end up with a 60. Now you could look at this and say, hey, is that 60 divisible by all of these numbers? 15, yes. 10, yes. 4, yes. So yeah, this would work. But again, if you don't understand it, if you don't see it, do your chart. And take one thing from every column. Is it necessary to write LCM every time? No, but
Yeah,
keeps in mind what it is you're doing, because you might be tempted to say nothing because you might have this idea down, doing the chart every time, and then you might be tempted to say there's no common factor. We don't care. We're not looking for it. In the case of this problem, do we have a common factor? No. Nothing's common to everything. Okay. Let's do one more of these guys. Next one is 20, 24, and 12. Factor trees. That's 2 and 10, which is 2 and 5. 2 and 12, 2 and 6, 2 and 3, lots of twos, all right. Well, 12 is just gonna look like that, 2 and 6, 2 and 3. I see they have a greatest common factor for sure, right?
Yeah.
Lots of twos. But let's say I'm looking for the LCM. Again, factor tree wise, start with the smallest factor, which is a 2. We have 2 here, we have 3 here, we have 2 here. Biggest of those is 3, so we're going to take 3. The reason for this is we want something where all of the factors can fit into it. And all of the factors aren't going to fit into it if I only have 2 of these 2s, because this one has 3. Next factor up, it's 3, none, 1, and 1, so we only need 1. And the next factor up is 5, 1 here, none, and none, so we need a 5. Now you can double check your work by looking at your factor trees and saying, hey, 2, 2, and 5. Do we have all of those? 2, 2, and 5? Yeah, okay. 3 2s and a 3? 3 2s and a 3, okay. 2 2s and a 3, well, definitely, right? All right, so if, as long as all of them are fitting in there, then we're done. That is it. This guy would be 8 times 15. It's what, 120, I think?
Yeah.
Yeah, cool. So let's go ahead and do a chart just in case. We have 24, 20, and 12. 24 was 3 2s and a 3. 20 is 2 2s and a 5. And 12 is 2 2s and a 3. All right, well. That's exactly what we had. So that means the first number that they would all have in common if I started multiplying them out is 120. Okay. So how are we feeling about LCM?
A little better.
A little better? And it's the same method. So if you know, that's one of the reasons why I picked this method, because we've now had twice as many examples as we normally would for one idea. If I looked at the greatest common factor, what would I have? A 2 and a 2. So the greatest common factor on this guy would be 4. You can always do both of them based on these charts.
Yeah.
All right, so we have about 5 minutes left. I wrote a bunch of examples for you guys to do alone. I'm pretty sure if I stopped and had you do them at the very end of the class in the last 5 minutes, no one would do it, or no one would be able to focus on it. So we're gonna go ahead and call it good. I am going to have you do some of these alone in the review on Tuesday. So keep that in mind, that it's not just gonna go away. You're gonna do it again, and you're gonna have to do it yourself. So, yeah, we're gonna work on that next time. We'll do a couple more on lowest common denominator and jump into percentages. Otherwise, you're done. Go home. Well, a bunch of you are already home. You two go home. I also get to go home.
Okay, bye, guys.
Bye.
Have a magical and wonderful evening.
Bye. Thank you, you too.
Don't cry.
No.
You got this. Hey, it's battery in my headphones inside.
You gotta run home?
I don't know, we'll find out.